Hi everyone and welcome to this session on NSO AJ Raft. I'm Kristian Larsson and today we are going to talk about AJ Raft, which is the latest AJ implementation available in NSO 6.1.2 and later. The agenda for today is rather simple. First, we're going to talk about the why. Why is AJ hard? Why did we go about implementing a new algorithm and what problem did we try to solve? Why should anyone use it and why should you use it? Second, once we're convinced about the why, we'll briefly take a look at how you can get started with running an AJ Raft cluster. The goal is that you, by the end of this session, is not only convinced of how formidable AJ Raft is, but that you also know what next steps to take. So without further ado, why? To explain why we need a new AJ algorithm, we need to talk about where the existing one falls short. And in order to do this, we need to start with the physics of the real world in order to understand just what makes building distributed, highly available applications difficult. So imagine you're a computer program communicating over the network. Now, communicating over the network is a lot like sending mail. You compose a message, you send that across the network, and we wait for a bit, and if we're lucky, we get a reply back. Now, this is the happy path where everything worked as it should. Since we got a reply, we can deduce that the original request we sent, it successfully reached its intended recipient. So we know that the network is working, right? The recipient then parsed the query, did some computation, and composed a reply with a result that, again, traversed the network back to us. And finally, we got the reply message. So all good. Now, instead, imagine that we send a message, but as we are waiting for a reply, there just is no reply. We wait and we wait, but still receive no reply. Now, what has gone wrong? Is the network down? Did the computer on the other end suddenly self-combust? Or did the application I was talking to crash? We pretty much cannot know. There are no reliable means of finding this out. The only thing we can do is to use a stopwatch to let the request time out after some time. So at the same time that we send our message, we start this timer, and if we haven't received a reply in 3 seconds or some configurable amount, we'll instead go into some error condition and take an alternative code path. But that is pretty much the only thing you can do. And I think it's crucial to keep this in mind, that getting that reply back or hitting a timeout, these are the only possible outcomes. And you have to base your decisions on that, right? So when we're writing an algorithm, this is sort of the only information that you can see, or that the only signals available to us. And we're not fighting against a poor implementation of the operating system, the computer that we're running on, or the network. These are rather laws of physics almost, but definitely facts and characteristics of the network and computers that we are running on. There are no reliable signals other than these, so that's what we have to work with. I actually like to imagine, you're sort of inside that postbox, and either you get the reply, and otherwise you're just like looking out that little hole and you can't really see much at all. It's really quite constrained. Now let's apply this to a normal NSO AJ cluster. So you have two nodes here. We got N1, the primary, on the left side. It's currently the primary, I should say, and it's connected across the network to N2 here on the right, which is the follower. So all updates are synchronously replicated from the primary N1 to the follower N2. And then we also have 3 clients, C1 through C3, and they perform queries, which are all handled by the primary N1. Now, imagine something bad happens to the network and we end up with a partition along this squiggly red line. So the left side of the network cannot talk to the right side anymore. And thus, the NSO, follower N2, cannot talk to the primary N1. And remember, all that NSO can do is send a packet across the network, and if it doesn't receive a reply within a timeout, it can deduce that something is wrong. We don't know what the problem is, but there is an error somewhere. The normal behavior in a 2-node replicating AJ setup is now that N2 promotes itself to become the primary. It does this because it didn't receive any replies, and thus it assumes that the old primary N1 is dead. Now we have this fancy diagram in front of us, so you and I know that this is a network partition event, and the best course of action would probably be for N2, which is in the minority, the smallest side of the partition, to just idle and wait to reestablish connectivity to the to N1, when the network heals, right? But again, the application, it cannot differentiate between network faults and the remote compute suddenly becoming unavailable because of a power outage or some other fault, right? And this is not an implementation bug or fault in NSO. So any distributed system that makes use of only 2 nodes will suffer from the same problem. So in our reality, with the physical laws we have, it's just impossible to know what has happened in cases like this. So the end result is that both N1 and N2, they assume the primary role and accept write transactions. So we have the C3 client being on the right-hand side of the partition. It starts communicating with N2 and sends config changes to it. Simultaneously, on the left-hand side of the partition, C1 and C2, they continue sending configuration changes to N1. So this is a split brain scenario. And in this design, we have a system that strives for availability. It wants to be available to respond to queries from clients, but it does so at the expense of consistency. These 2 NSO nodes, they're both actively serving both read and write requests, which means we will become inconsistent. We have effectively chosen availability of the system over consistency. And I would argue that if NSO or any stateful system, like a database, is inconsistent, it can't do a very good job. We cannot rely on NSO to correctly provision network services if it is working with inconsistent input data. And so consistency in our data is paramount. We must have consistency. The CAP theorem is it's a paper published, Eric Brewer, I think. It lists 3 properties for distributed stateful applications, right? So we have consistency, availability, and partition tolerance. And we can only choose 2 of these. So partitions, they're not really a property of the system, but rather a fact of reality. As a distributed system, you have multiple computers and you can partition them, right? We cannot guarantee that they never partition. So as a distributed system, we must be partition tolerant. So the CAP theorem is sort of like pick 2, but one has to be P. So either we're going to pick an AP system, which is available and partition tolerant, and that is exactly what we had with the 2-node setup, right? It prioritizes availability to the detriment of consistency. Or we pick CP, that prioritizes consistency over being available. So what does that actually look like? Well, this is where Raft finally gets to make an entrance. Now, Raft is a consensus protocol, which basically means it does a form of voting. And as you can imagine, one of the more basic problems of voting is that you can end up with a draw, right? So this is why we use an odd number of nodes. 2, like we had, it's not an even number. 1, well, that's not even a distributed system. So 3 is the smallest number of odd nodes that can possibly work. So the quorum, or majority really, in such a cluster would become 2, right? And that means that we can also tolerate the loss of 1 node and can remain up with the remaining 2. So the availability of this system is really the same as the 2-node one, right? We achieve the same fault tolerance level by adding the 3rd node. Now, Raft is not new. It's published 10 years ago, right, in 2014, but it really relies on the same principles as described by Paxos. So we got view stamped replication, which are really quite old. They were published in the late 80s. Raft is a bit of a simplification of these, and it's the protocol that we've chosen to incorporate in NSO-AJ. And so that's what you get when you enable NSO-AJ Raft. And let's just look at what that looks like. So here we have client 1, C1, sending an edit config request to N1, which is our primary NSO. NSO then does some work, like running service create code or similar, and the output is a diff of the changes from the transaction. So we want to distribute this diff to the follower nodes. So we sort of make this copy and prepare to send across the network. We also want to keep track of how many positive acknowledgements we got on back. There are 3 nodes in total, and quorum is at 2, right? And obviously, we can count ourselves as 1. So we need to hear back from at least 1 other follower in order to make progress on this transaction. So we send those packets across the network, right? And here we can see the first packet has reached its destination, N3. It persists the data locally. It then composes an acknowledgement reply that it sends back to N1. N2 is a little further away with a higher network latency, so it still hasn't received its message. Let's continue. And there we go. So N2 receives its diff and does the same thing. It persists it locally, it prepares an ACK message, and then sends this back. And by now, N1 has received that first acknowledgement from N3, and thus now we reach quorum, right? We have 2 out of 3. We also persist the change on the primary, and now we can send the reply back to the client, thus acknowledging the overall transaction, right? And last, by now, we've gotten the third and final ACK from N2, which it doesn't really make much of a difference by now. I mean, we already sent a reply to the client. The transaction has gone through, but nonetheless, we now know that both of our followers are in sync with us. They're both sort of caught up, right? And agree on the transaction history. Now let's consider what happens during a network partition. So client 1 sends an edit config request. We start by partitioning the network. Then we got that edit config request just like before, and NSO doesn't work. We prepare those diffs. Now imagine the partition happened a millisecond ago, so we don't. N1 still thinks of its followers as alive. It hasn't realized that they are not reachable. We keep track of the number of replicas, and then we start sending these packets over the network, right? So N3, again, it receives the diff, it persists it locally, prepares an ACK reply, and is going to send it back. Now look at the packet going to N2. Well, it just goes into the abyss, right? The network partition, somewhere in the network, we just drop this packet, right? We continue. The ACK from N3 reaches the N1. We now have 2 out of 3. We persist it to disk, and we can reply to the client saying yes. So we can see that we can, in fact, tolerate the loss of a single node, right? 2 is a majority, and thus the cluster will continue operating. If we add a second failure, so we have that network partition again, but the nth node is now also out of service for some reason. So it could be a power outage, the server suddenly stopped, or someone is doing some administrative task to it, right? And again, if this just happened, 5 milliseconds ago, N1 will still think that N2 and N3 that they are alive and well, but as it tries to get acknowledgement on the transaction diff, both followers will time out. So client sending an edit config, we do the work, prepare those diffs, count ourselves as 1, send these across the network, and they disappear, right? So without a follower, we cannot make progress, and N1 is all alone here. It will simply wait until it can re-establish communication with the other cluster members. Meanwhile, it is waiting. So this underlies an important fact of operating an HA Raft cluster. You must have more than one node. You cannot operate on a single node. You need your quorum in order to proceed. In this case, we had double failures. So we're already at a point, where you would, if you were to compare this to classic HA, we already have more failures here. And you can expand, right? You don't have to run 3 nodes. You could actually run 5 nodes instead. Now, I would. We in all of our testing with system validation, etc., we are focused on 3 nodes for now. So that is the recommended approach. If you're interested in higher availability using 5 nodes, then I would suggest that you come talk to us first. But it's it basically the support is in there, right? So, through all of this, Raft, it really does solve the problem of split brain. So if you restart your cluster, the nodes, they need to reestablish communication. They do a voting round to elect a new leader. And since we are guaranteed to only perform transactions in the cluster when we have a majority of nodes, it means that at any given time, the majority of nodes will also agree with each other, which is the latest transaction. So it's always clear which nodes are further ahead in the transaction history, thus making them eligible to become the leader or primary. And this is what makes it safe for split brain. Recovery can be completely automatic, and it's just very many good things emanate from the safety that we get with a consensus protocol. I also want to touch upon deployment, right? So it's sort of a very practical part of deployment. So if we look at modern sort of cloud environments, we have here, in this case, this is Azure. So they have something called regions. So region is fairly small or contained geographical region. You think in the hundreds of kilometers typically. So, like a millisecond or so of latency. And within a region, you have multiple availability zones. So here we have 3 of them drawn out. And if we're going to deploy NSO, we would deploy an NSO instance in each availability zone, right? So that means we don't have any real shared single point of failure. I mean, on the other hand, if you were to deploy, say, 2 NSO nodes in one availability zone and that one goes out, well, obviously, then the whole cluster will stop, right? Because we only have one remaining one. Similarly, in AWS, we have regions and availability zones, and the deployment of NSO would look quite similar, right? Google Cloud, same thing, pretty much. They have regions. They don't call it availability zones. They just call it zones. But you have multiple zones that do not share faith. They don't have, shared points of failure, really, right? So again, you would deploy your 3 NSO instances across those different zones. Besides the strong consistency, which I think we've now gone over, and the guaranteed durability that you get with it, there are also some other benefits to using Raft HA. I think the TLS encrypted transport is definitely one of them. So in untrusted or adverse network situations, you can now use encryption, right? We have fully automatic operations, and again, I think we went through that a little bit here with the way that we do leader election and just the way we perform every transaction, right, requiring a quorum. It's a lot more safe, right? And that means that we can recover without manual intervention for error recovery. So that's really quite nice. And all of this comes together, I think, to make it a lot more cloud friendly. And again, I mean, you don't have to actually run it in a public cloud. I think, to me, cloud friendly here just means that, you run things in a certain way, and it's sort of with certain tools, and it's easier to do that. Okay, so let's jump over to configuring it, right? And I'm going to switch over to my terminal here. So I have here NSO 6.2 fresh off the press as a local install on my machine. And in it, in the examples collection, we'll find high availability Raft cluster, and in there we have a demo shell script that we're going to run. And I mean, the cool thing here is that it's included in the examples collection, so you can run through this again, and I really encourage you to do that. So step 1, just resetting that example. Step 2 is creating a self-signed certificate authority. And we're going to use this for both authentication as well as encryption. We mentioned earlier how the transport between the nodes in NSO HA Raft is based on TLS. And TLS uses certificates for authentication and encryption. So we need to create those certificates, right? I must point out that it is absolutely crucial that you use a self-signed certificate authority here. Because we use it for authentication, that means that when we load in a CA, the NSO node is going to trust other nodes that present a certificate signed by the same CA that we trust. If you were to use this, and this is different than how it's used on the internet, right? So we have public CAs that are used for all web servers and all these public-facing services. If you were to take one of those public CAs and install it into your NSO, that means that any certificate signed by that CA would be able to authenticate towards your NSO. NSO would trust it, right? So that means any web server on the internet signed by a public CA, it would take its certificate, start talking to NSO, and it could do all sorts of things, right? So you don't want that. You must use a self-signed CA. I'm going to press enter here and let it proceed. It starts by creating the CA and then the certificates for each node. So that goes by 3 times, right? And it's essentially this thing that it's doing, right? One private key and certificate per node. We also see a bit of the configuration here, but we're going to get back to that. It's actually going to be modified in between here. So let's see that in a second. Next step is setting up these NSO nodes and putting in the configuration. This is where it does that modification of the config. So let's actually look at it now. And here we see a part of the ncs.conf on node 1. So we have the HA Raft section. It is enabled. We have the cluster name, Stockholm, followed by the node address. So this determines what we're going to listen on if there are multiple addresses. And it's also an identifier for this node. So this is going to be different for all the different nodes involved in the cluster. Second, we have seed nodes. And seed nodes, I think, is a really cool feature in NSO-HA Raft. So it means that we don't have to list all the nodes of a cluster. We just need to give it a seed node. So when it starts up, we're going to connect to the seed node. We're going to start talking to it and ask it and discover all the other nodes that are connected to it. And then we're going to establish a full mesh. So all nodes are going to have a TLS connection to all the other nodes. So I think this is really neat. It's not very complex right now. I mean, we only have 3 nodes, and you set that up. You might as well list them all, right? But as things can become more complex when you do upgrade maneuvers and things like that, this could come in really handy. And it's yeah, it works in principle. It's really nice, right? So we're gonna go ahead, and next step is to start up the NSO processes. I'm running all of this on my local computer. This is what this demo script does. So there are no containers, no virtual machines or anything like that involved. It's just 3 processes running on my machine. And by now, I can actually connect to one of them and show HA Raft and look at the status of this. So the role is stalled, which means that it's not doing much of anything. And that's because we haven't told it what to do. We can, however, see that it is connected to the other nodes. So we are on N1, and it's connected to node 2 as well as node 3 in this cluster. And this is because there's like 2 level the cluster is sort of on like 2 levels. So there's the underpinning, the low level protocol here of just establishing connectivity between all the nodes, right? So this is the TLS part that I'm talking about, and it's really the protocol here is distributed Erlang. So it's a protocol that you use to talk between distributed nodes in an Erlang system. And the connected nodes, they convey what that looks like. So here we're on N1, and we are connected to the other 2. We're going to see in a second when we establish the actual HA Raft cluster that we get a second list here of members. So let's go ahead and do that. We're going to run the HA Raft create cluster action. It is going to include itself. So I'm running this on the N1 node. So it's going to include itself. And in addition, we add the 2. We have members here like a list. So node 2 as well as node 3. So all of them, right? And actually the next section here is looking at the HA Raft status of all the nodes. So now we can see this is on N1. So this is the same as we had over here, right? It was stalled. I can run that again as well. It is now the leader, right? And this is where we can now also see membership. So members are members of the HA Raft cluster. And so this is different from the nodes that are connected in our connection layer, right? Usually it's the same like here, but it could potentially be different. And we see the same thing, right? So for N2, it's now a follower, and the leader says node 1. Same thing with N3, it's a follower, and N1 is the leader. So all good. And let's also just show now, because the next step is about loading a package, that currently we don't have any packages loaded. So we're going to go ahead, add in this dummy package, which it is an NSO package. It's just called dummy because it doesn't do much of anything. And then we're going to reload, do a package reload. And I think this is a really neat feature of NSO-HA Raft because the whole cluster effectively acts as one logical system. So when we do a package reload, we don't have to be concerned about taking the packages to the different nodes and like doing package reload on all of them. The system acts as one logical system. So we put new packages on the leader, we issue a package reload, and HA Raft is automatically going to distribute this to the other nodes and load that in to the NSO system. So let me quickly switch to N2, and we can look at the packages there, and we see, yep, this dummy package is loaded there as well. Next up, we're going to add some configuration and we do this to node 1, which is the leader. So here's that configuration. And we can see we added it to N1. All write transactions must be performed on the leader because it's the node that leads all the work in the cluster. After that, we now check the dummy configuration on other nodes. So we have N2, that's the same configuration, and N3 with the same configuration. So this is exactly what we saw before, right? The leader leads the transaction, computes the diff, distributes the diff to the followers, which then apply it to their database. And so we have a uniform view, consistent view across the whole cluster. Next, we are going to fail node 1. So let's just bring that down. Now, all the nodes in the cluster, they continuously send keep alives to each other. And through this mechanism, they will discover if any of the nodes become unavailable, right? And that is exactly what happens here. So node 1 was the leader, right? This is what we started with. And it becomes down after we stopped it. And then node 2 and node 3 are going to run another election to elect the new leader. And so when the node 1 disappears, they're going to start a new term. It's actually called a term, an election term, and they're going to propose that they themselves become the leader, right? So they go into this candidate mode, say, I should be the leader. There's a component of theirs where we look at where they are in the transaction history. So in order to be eligible to be the leader and get a vote from another node, you have to be at the latest step in the transaction history. If you're behind another node, that means you're automatically not eligible to be a leader, and you gotta like step down and possibly vote for the other node, right? And in this case, we know that the cluster was whole before this, so both of them are eligible. It's more or less just a race. And that's also interesting to note that there is no automatic sort of or built-in determinism in that, you know, one node has priority over another node to become the leader. It's more or less just timing based. So it is a little bit racy, at least among the eligible nodes, right? In this case, node 2 becomes the leader, and so node 3 is the follower. And now we can add some more configuration. Since node 2 is the leader, that's where we go. We add in a bit of new configuration like this. And then we can go look at N3 and see that indeed, here we have this new configuration. So this shows that the cluster is operational. It accepts write transactions and process them correctly, even though we're down to 2 nodes, right? And this is as it should, because quorum in a 3-node cluster would be 2, and with 2 nodes we can operate. So the fault tolerance is 1, the loss of 1 node, right? Now let's so let's also just show, okay, so from the N2's perspective, the current leader, we don't see the N1. I mean, I can try to start the CLI. We just see that this node is down, right? So now let's start node 1 back up again. It's going to take a second, and then rather quickly, now if we look at N2, we see that, yep, when node 1 starts up again, it's going to reconnect to the nodes that it knew about before it crashed or was shut down or whatever. So it sort of remembers that, right? And it's going to connect to those again and check in, and then it's going to find out, okay, so there is a leader in this node. It sees if it agrees with the transaction IDs and all of these things, right? Which it is in this case, because it's the existing cluster is the majority. And so it's going to connect to that as a follower, and then do a catch up on the transaction history. And that's what we'll see here in the final step, that now if we look at N1, the data that we added in last is also visible on N1. And once again, I want to point out, right, that, you know, N1 is it is a follower, so there's no inherent priority in that, oh, node 1 should be a primary whenever it's available. It's not like that, right? So now the cluster is stable with node 2 as the leader, and it will remain as the leader until there is some form of event, like node 2 goes down, or some other reason to why there would be a new leader election. Okay, so with that, I would like to conclude this presentation. Once again, I think it's quite amazing how this new core piece of technology has been implemented in NSO. NSO is a well-established and mature product by now, so sort of ripping out the guts of it and adding in something like HA Raft is really quite cool, I think. And HA Raft effectively addresses issues that we have with, in general, with odor replicating HA technology, and it enables a robust and safe mechanism for high availability of NSO. So it really is what you want to use in your HA deployments. So please check it out, and thank you so much for listening.